Welcome to join with me the lecture on stability condition, and of course the course is still laser physics, and as I warned already in the previous lectures, we will now outline to you the mathematics, how we can understand how a laser non-configuration can be stable. So this would be then the mathematical tools to understand, for example, why Fabry-Perot resonator, so that would be just a resonator formed using two planar mirrors, is not always a very optimal configuration because it doesn't result in a stable laser configuration, and that kind of motivates in real laser resonators to work with curved mirrors. So that's basically the motivation. We want to understand the piece of mathematics so that we can really start designing, or at least we could start designing proper laser resonators. So, stable cavity. That's really a key requirement for making a laser. So that's our motivation for this lecture. And what are the conditions for stability? Well, after an arbitrary number of round trips, the rays of light still need to find itself or themselves in the vicinity of the optical axis. So basically what this means physically is that we need to have light remaining guided inside the cavity. So basically rays of light need to be bouncing back and forth within the cavity mirrors, and also in a repeatable manner, so that we can say that the laser cavity is stable. And here we are really relying on the paraxial approximation, on the geometrical optics approximation. So we are really assuming that our cavity is quite large, quite long with respect to the kind of a size of the beam propagating, so that we can really approximate that our light propagating within the resonator can to a good degree be approximated using geometrical optics. So basically paraxial approximation holds. And now this condition for stability basically quantitatively can be studied by looking at the ABCD matrices and forming ABCD matrix or matrices for the laser resonators. And of course, intrinsically, like I was just saying, we are relying on geometrical optics. So we are relying on paraxial approximation to hold, so that we can really describe everything using ABCD matrices. And now we are really interested in describing the ray propagation through a single round trip, because then we can multiply the round trips to many round trips and try to see, do we have a kind of repeating pattern forming for the propagating ray bundles. The output ray after n round trips then will be given by a piece of mathematics, so that's the output ray, and then we have a ABCD matrix telling us how does a single round trip change the input ray, and then we are multiplying that to the power of n, where n is now the round trips. So it's not a multiple of integer of a how many path lengths we have a light propagating within the cavity, or it's certainly not the refractive index, but rather it's the round trip number. And in this ABCD matrix formalism, of course, we have the input ray then on the right hand side of the matrix, ABCD matrix. So let's now calculate the nth power of this matrix. And how do we do that? Is that we use the infamous Sylvester's theorem. Please Google more about this. We don't really go into the details how this works out, but we just take use of this piece of mathematics. And now we can write this kind of a power expansion or nth power of a matrix simply using this kind of a sinusoidal trigonometric forms, where this theta will be given in shortly. So basically, by using Sylvester's theorem, we can really write this kind of a power of a matrix ABCD in a form of sines and cosines and these original components. So this would be the first component. So we have these kind of weird looking terms here. Then we have the B term here times sine of n times theta. Then we have the C term also modified, and then you have finally the D term modified, and n here is the number of round trips physically. So this defining angle theta is given by cosine of theta. That's 1/2 of the trace of the matrix ABCD. And this is basically given by this kind of form, A plus D divided by 2. So if you're really interested, I recommend that you Google about this, or these days you chat with an AI and hopefully you will get the right answer, or at least kind of like a believable answer. And you will see that you can really apply Sylvester's theorem for this case to calculate the kind of power expansion, or kind of like nth power of a matrix. And in the limit of n approaching infinity, the system should not diverge. And this is in a way what we physically require, that what is a stable cavity configuration. So this is what we kind of like say, that this is the requirement we need for the cavity to actually be stable. And in this case, we can calculate the limit of this ABCD to the power of n, and then this should not be infinity. So that's basically the kind of requirement that we must have a stable cavity. So basically this then implies that this angle theta must be a real valued number. And this is a beautiful thing, because now we can really take use of this, because the reality of angle theta then implies that this cosine of theta doesn't explode, so that really is being bound with these limits. So now we know that cosine of theta, if theta is a real valued number, it will be oscillating between minus unity and unity. And now we can plug in the trace of the ABCD matrix, so that we can replace the cosine theta with the trace of the matrix. So we have this condition, and finally we can write things in a more simpler manner. So we have the modulus of A plus D components of the matrix divided by 2, and that must be smaller or greater than unity. So this is the stability condition we are looking after. We want the resonators to be stable also in practice. So let's just consider the case that we have these values smaller than unity, instead of like being possibly also equal to unity. And the limit value of unity is only marginally stable, and right now we are not interested in that kind of cavity configurations, although there are cases where you actually want to be forming a marginally stable cavity. But more on that later in the upcoming courses on mode-locked lasers and Kerr-Lenz mode locking. So a very general outcome of this is that we can apply this kind of piece of mathematics to any resonator of interest. And once the round trip matrix has been calculated, then we can really calculate the nth round trip, and then we can see what is the stability condition for this kind of cavity. But there is a second criteria that this is valid for the case of a curved mirror. So this is basically kind of like a way we can simplify the piece of mathematics. So we can really define these kind of new variables, so-called G parameters, and they are defined as 1 minus L divided by the reflectivities of the mirrors. So this is another way of saying what is the stability condition of a laser resonator. And this really works beautifully when we have curved mirrors. And using these above defined G parameters, we can really simply write the stability condition. So this is what we had before, in a way that the G parameters are in between 0 and unity. And this gives an alternative stability condition. And let's now prove this statement about the G parameters. So for resonators described above, the ABCD matrix for a single round trip can be written that the ABCD matrix is of this form. So we have a first mirror, we have the ABCD matrix of a first curved mirror, then we have a propagation within the cavity of length L, then we have the second mirror, ABCD matrix of that, and again we have propagation within that cavity of length L, and that gives us a round trip. So basically we can plug in the values, we can calculate all of those matrices together so that we can form the overall ABCD matrix of the whole round trip, single round trip. So this is how it looks like. So basically we are multiplying all of these matrices together to have something like this. And since in the stability condition we only care about the A component of the ABCD matrix and the D component of the ABCD matrix, I'm not showing the B and C components, but maybe that would be a good homework exercise for you to make and calculate in all its glory this kind of 4 2 times 2 matrices together and see what you get out. In any case, the above results gives us a stability condition so that we have 1 over 2 times A plus D. So that's the original stability condition. And now plugging in the actual values for A and D, we get something like this out from that piece of mathematics. So this is basically the kind of stability condition. And now the kind of beauty for the G parameters starts like coming visible. So finally we can insert the definitions of the G parameters. So the G, recall, was defined that it's 1 minus L divided by RK, where RK is the reflectivity of a given K mirror. So that's basically what we can plug into the above equation, and we can get a little bit simpler like a piece of a mathematics. So something like this, and we can really like simplify that this ultimately will be 1 minus 2 times G1 times G2. And now I realize that I actually have a typo in the previous lecture slide, so that the kind of stability condition actually should have the two G1 times G2 factors there. I think I only had like one G2 factor there. So now we can finally write that we have this stability condition, and we can write this now using the G parameters so that it looks like this, and ultimately we can get the actual final stability condition. So that's the kind of second condition. And this is nice because it gives us a kind of graphical description of the stability condition. And now I will correct myself in the kind of like notes in what follows, but in the previous slides, I think I only had like G1, 2 between the 0 and unity. So of course we should be multiplying like a G1 with G2. So I will be correcting that mistake. And please don't be confused yourself if you only watch this lecture. And now, since I promise that this helps us to write or form a graphical description of the stability condition, we can write and we can draw these kind of figures. So basically the stability condition using the G parameters, so mathematically that's this, so that the G1 times G2 is between 0 and unity, and the G parameters are being defined that it's 1 minus L divided by R1 or R2. So we can now really plot the stability condition into x-axis corresponding to G1 and y-axis corresponding to G2. And now we can really like understand how a general spherical resonators would be formed and how stable region would be within that blue region. So this is basically how we can now graphically understand that what kind of cavity configurations using spherical mirrors and possibly plane mirrors would give us a stable cavity configuration. So this is nice. The dotted curves here correspond to the case of possible confocal resonator configurations. And then the line ABC there in that figure corresponds to special cases of symmetric resonators. So the A case there in that curve or figure corresponds to the concentric resonator. So basically that was the case we were considering before. So in that case, the two radius of curvature R1 and R2, they are identical and they are separated basically for a given length. So these are basically then given by the cavity length divided by 2. And then B case is a so-called confocal configuration. This is also very commonly used. And in this case, the curvatures are slightly different, so they correspond to the length of the cavity. And then the final case would be the C, which is the planar Fabry-Perot case, where we don't have curvature at all. So basically R1 and R2 equal to infinity. So that would be that point there. So this is the marginally stable case that we are already at the interface between the stable region and the unstable region. And in case you're wondering, this might be confusing, maybe we just should look at this confocal scenario here. So it looks to be at the origo, but please remember these are the G1 and G2 parameters. So plugging R1 equals to L and R2 equals to L into the definition. So we have L minus L unity and 1 minus unity equals to 0. So that's where we are having this confocal case at the origo of G1, G2 axis. So that's the kind of what happens here. So don't get confused somehow that there's a mistake in these slides. For now, there isn't. So this is basically the approach, how we can calculate the kind of stability condition. We can understand how some configurations are stable, and we can even understand that some cavity configurations are more stable than others. So for example, we can now even understand these marginally stable cavity configurations where we are really close to the edge of the stability region. And many times you want to have your laser somewhere like more firmly in between at the stable region, so that small deviations, small temperature variations, more small misplacement of your mirror orientation, and these kind of different things that in practice will be there when you are making real cavities, don't really like mess up with your proper stability of the laser resonator. So this is basically what I want to say, and please remember this figure. It's a classical figure showing how a stable cavity configuration can be found by playing around with the G parameters. But now I will thank you for your patience for following me through this lecture, and then please stay tuned when we are talking in the next lecture about the eigenmodes of optical resonators. So we are now really extending more into the actual kind of mathematics to understand how does the field distributions actually look like within the cavity. But here I will stop my mumbling here. I thank you. I wish you a pleasant day. Goodbye, good night, good morning, and then please join me quickly for the next lecture. Thanks and bye-bye.